So I am Shivam. So in this homework, we have created a GraphRAG continuous pipeline. So basically, we have a stream of chunks, and we are extracting concepts relationship between them, and storing them in a Neo4j graph database. So we are doing the streaming via Flink streaming platform, and for initially all our uh, chunks are stored in this JSON file. So basically, uh, Flink will read these chunks as a stream from this JSON file, and then it will operate and store them in a Neo4j database. So let's go step by step. First of all, for the deployment purpose, uh, I have So these are step by steps how we have deployed this in this whole streaming application in our EKS cluster. So first of all, we create the ECR registry. So ECR is AWS elastic containers for containing the Docker containing the Docker images. So as you can see here, uh, yeah, this is a graph. This is the image of our Docker build. So we built the image and stored it here in the ECR registry. So you can see it here. So this is the terminal where I have run all the commands to create containers, ECR registry, and EKS deployments. So let's first see how I created the ECR repository. So here you can see first I get the ECR repository with this GraphRAG Flink name. After creating that, I before that yeah before that I first build the Docker uh, build command to create. So it basically takes the Docker file stored in our local, and it uh, build the image out of that. So this image will contain all the entry points for our this GraphRAG application. So basically the aim of this is to basically run the job and to fetch the to fetch the chunks and create a stream out of that, and then store all the concepts and the relations in a Neo4j. So all of that information will be present in one jar file, and we are creating the image out of that jar. Uh, so then after that, we tag the image here, Docker tag, and then this is the important part. So here we push the image into the local into the ECR repository. So uh, that this is the image you can see here. Uh, yeah, this is the image you can see that I have pushed from that Docker push command. Then after that, once the image is pushed, we create the EKS cluster. Okay, so now comes the EKS cluster creation part. So we have basically named this cluster as this GraphRAG cluster. Then in region US East one, we have uh, node type of T3 X large, and total nodes will be start with three, and it can go minimum to two and maximum to four. So it is auto managed by AWS. So basically, it will auto scale to maximum four and minimum two. So let's see how we created that. Yeah. So here you can see we created that EKS cluster by this command. You can see it is getting created. EKS cluster is ready. So you can see it here also in AWS console. So yeah, this is a cluster that I created. After creating the EKS cluster, we first enable the IAM roles for service account IRSA. So this is a crucial step. It basically allows the Kubernetes boards to assume the AWS roles. So we do that in this step. So you can see here via this command we have created this OIDC, and so it says that it created an OpenID Connect provider for cluster. So basically now AWS, so this cluster can assume the AWS roles. After creating this, we create a service account. So we created a dedicated 2 minute service account named Flink, and basically it linked and basically we link it to an IAM role, so it grants all the S3 access and all the basic access that it needs. So here we do it in this step. So you can see here in the command line. So yeah, you can see here we created that. So after this, we add basically a certificate manager for the Flink operator that we will use. So this Flink operator is crucial. So this operator basically we add the chart for this, and this operator basically will manage the job manager and task manager tasks. So it will auto manage the all the ports for job manager and task manager. So we install it here. So this via Helm command. So it will install the charts and install it in our cluster. So here, uh, 1 second. Yeah, deployed. So first we have to deploy the certificate manager, and then once we deploy the certificate manager, then we install the Kubernetes operator, Flink operator. So here you can see it is deployed. Doing that, we add all the Kubernetes secret, all the application secrets like username, password, and all the configurations to the config map and secret manager. So we do it by this. Second, and see here, I am adding all the secret and all the configuration. So you can also get the config map, and you can see all the certificate, all the configuration here. So basically, up till this point, we have created all the configuration required for the EKS cluster. So after this, we have to deploy our deployments. So first deployment is we deploy the Olama as a daemon set. So it ensures that Olama instance runs on every worker node to handle the LLM request from our Flink tasks. And then finally, we deploy the Flink deployment manifest. So it submits our GraphRAG job to the newly created Flink session cluster for execution. And after that, finally, we also apply this kube CTL port forward. So basically, it creates a tunnel between our local computer and the EKS cluster, so we can so that we can access our this Apache Flink UI through our local host, so 8081. So basically, it creates a tunnel. So you can see here all the deployments, how I deploy in the terminal. So first of all, you can see this deployment of Olama, and then here it is getting deployed, and then um, we can see here I deployed this uh, Flink deployment, and this is all the deployments I have done. So basically, all these steps basically creates. First of all, we created a Flink operator. So if we go step by step, first of all, we created a Flink operator. So Flink operator using Helm. So basically, it will manage our cluster state. So it will manage the task manager and job manager pods with that we have defined in our job graph RAG YAML. So this YAML file basically contains the job manager and task manager pods. So that Flink operator will operate on these pods and will manage these pods. So that's how it works. And this Olama daemon set basically it runs on every worker node, and so that Olama is present everywhere in every node pod. So I deployed this around like around 3 hours back. So we can check the how it is working here in the Flink dashboard. So in this UI, you can see various metrics like how many bytes are sent in each parallel steps, how many parallel steps are running, what is the latency. In the timeline, you can see the various latencies and how many checkpoints, like which step failed in execution, where it failed. So you can see all these metrics here. So you can also go to this Neo4j dashboard as the pipeline is running. So here it shows how many nodes it has created, how many relationships. So we ran for around 300 chunks. So far it has created 2000 nodes for as of now. So let's see how it looks. So basically, it gives the summary. So it has these many nodes, chunks, and concepts, and it has these edges. So these are the edges basically. So mentions relates to co-occurs. So if we create any of this like concepts, and if we see like for first 100 concepts, if I run this, so here you would be able to see the surface, basically the concept id, what that concept is, the origin, like it is getting from the llm has produced this concept, the lemma and the surface. So you can see the various concepts here. So that's how we ran our EKS cluster job, and it creates all that different uh, graph data structures. And we can also, now we will go to the REST API query part. So we can also query this graph data base through REST APIs. So we can define various API like query API, where user can ask any query like what is this database optimization concept, and like how it is related to like any query. So basically then what we will do is we will use LLMs to fetch all the concepts from that user query, and then we will create a custom query which using this match keywords and all this, and then we will ask this Neo4j API on the basis of the created query from LLM, and then we whatever response it will give, on the basis of that response we will refine that response using LLM and give the response back to the user. So basically, LLM will tell like how this concept related to other concepts, what are the nearest neighbors of this concept, what is the evidence that this concept is related. So all those things we will get from the Neo4j, and then we will refine that using LLM, and then we will provide the final answer to the user. So now let's move to the REST API part. Various APIs for this query to the Neo4j, and I've deployed it basically in EC2 in front of load balancer ALV. We can also deploy it in front of AWS API gateway. Yeah, so one of the services query service. So here you can see in query we can give the request like what is the software artifact is Mac OS based upon. So it will go to first what it will do, it will first extract the concept out of this query, and once so that part is done by LLM. So LLM would extract the uh, concept out of this query, and once the concept are extracted, then the backend would create the cipher queries, the match cipher queries for the Neo4j. So whatever results the Neo4j gives, and then again that would be refined by the LLM, and the final answer would be given to us. So for example, this is the answer. So it says Mac OS is based upon BSD operating system. BSD has several variants. This is this. So it also provides us the paper it has looked upon. So paper ID is this, the title of the paper is this, the concepts, and this is important. So it also tells what are the different concepts that it has looked upon for the answer. So these are the different concepts, and also the citations. So these are the like the evidences, like these are the chunk IDs from where it has got the answer. The proof in actual DB, Neo4j DB, that the our LLM is not hallucinating. It is actually getting the answers from the Neo4j itself. So, for example, for the question like software architect Mac OS, so you can see that software architect is one of the concept. Software architect and other concept is it is related to the Mac OS. So you can see this is in on the uh, relation edge. So you can see both Mac OS and software architect is related, and this is the important part, the evidence part. So evidence so you can see representative of such a family of BSD operating system. So basically, it is saying that the Mac OS. All these three OSs like Mac OS, Sun OS are all part of the BSD operating system. So that's why it got the answer that Mac OS is based upon the BSD operating system. So once it gets this evidence, so Neo4j will provide this evidence to the backend. So backend will then refine it and again go to the LLM to refine that response and then give the final response to the uh, to us. So similarly, then provides the proof like this concept IDs and chunk IDs on the basis. Again, like one more thing. So also I have provided the papers, so you can also verify this from here. Like this is the title of the paper, and same this is the chunk text that is provided as evidence by this Neo4j. Uh, yeah, this is a chunk text that is provided as evidence by Neo4j. You can see. Yeah, that is it. And again, other query that I have given is this is the important query. This is basically explain query. Explain. So it will explain what are the different steps taken by the request. So for the same query, like what software architect is, so I just give the query name, like what software architect is Mac OS based on. So it will provide the actual query plan. So how did it plan the query? So first step would be the extract concepts. So here the LLM would extract the concept from the query. Then the second step would be the find matching concepts. So in this step it will create a cipher. So in this cipher, it will whatever concept it has extracted from above step, it will pass upon to this cipher and will get the results. So it shows that found two matching concepts, software architect and macOS, like I have shown you in the graph database. After this, the other step is get the relation. So once it gets the concept, it gets all the relations of that concepts. So like for that, it creates this cipher that to concept is in this concept IDs. So this is how it creates a cipher and gives whatever result now we get is then we expand the neighbors. So once we get these concepts, we also try to see what other concepts are related to these given concepts. So it shows that found these concepts which are also related to the given concept. So the final answer would be the combination of all this, and we will provide all this information whatever we have gathered in our steps to the find LLM, and it will basically refine the answer, and it will give us the final answer. And also this is the evidence, it also provides the evidence, so the chunk IDs from where it is taking the text. So that's the plan it the backend takes. So this whole thing is the how the backend plans the query execution. So this is other API that I have created, which is the neighbors API. So it will basically you give the concept ID and it will get all the neighbor, basically the nearest neighbors of the that neighbor. So for example, if I get give software architect, so it will go to this Neo4j database, and then it will see which are the concept IDs which this software architect is related to. So it will get like BSD related to software architect, Mac OS related to software architect. So other also, so we can, there are all other concepts also that are related to this, but we have only given in the backend that show that two top concepts for this. The other API, this is the evidence API. So here we whatever the evidence we get from this uh, evidence text that we get from this API, the query API, we pass that evidence text to this evidence API. So it basically gives the paper IDs and text, the actual text that is present associated with this evidence ID. So this I have already shown you that it is taking the evidence from this paper mining evolution data paper ID, and paper ID is this the basically the name of the paper, this 101 PDF. This is the paper ID. So document ID, yeah, this is the document ID. Yeah. So finally, I have given this get job status controller. So basically, you can give the job ID and it will give the status is running or not. So basically, it in the backend it asks the Flink API. So yeah. if I want to quickly summarize, so basically we built a graph rag pipeline, continuous pipeline. So basically where we stream the chunks from the JSON, and then Flink operates on those chunks and uh, creates nodes, various nodes like concept ID, chunk IDs, and stores various edges between those nodes into the Neo4j database. So basically, we build the kind of knowledge graph in that database, and after that, we create various uh, APIs to query the built database with the help of REST endpoints. So, and yeah, that's all about the project homework. Thank you.